start the recording here. Okay, one moment. Before we get there, I want to go back into that ebook real quick. Okay, so once again, let's just remind ourselves what we learned here. Power series is a series of the form n equals 0 to infinity of c sub n times x to the nth power. If you expand the terms out, you get c naught plus c1 times x plus c2 times x squared plus c3 times x cubed and so forth. So this series is a function of x. The coefficients, the c's, are found by a formula, and the power series now is a function of x. Okay, and we call it a power series. Power series may converge for some values of x and diverge for other values of x. So what we're doing is we're saying, let's take the power series. I mean, could we take the power series and set it equal to a function? And the answer is yes. I mean, we want to do that. We want to take the power series and ultimately set it, well, the idea is, what if a function, some function of x, could be written as a power series? That's really the direction we should go. Okay, you're going to learn tomorrow in section 8.6 how to take certain functions and write them as power series. So let's assume that we can take a function and write it as a power series. The question is then, for what values of x would this power series be true for the function? For the function of x to equal the power series, it's only going to be equal to the power series for values of x where the power series converges. So it's essential to find this interval of convergence. Okay, and what they did in the book was they let in the power series, they took an easy example, they let all the coefficients equal 1, and so the power series becomes then the sum where n equals 0 to infinity of x to the nth power, which is 1 plus x squared plus a, all the way up, you know, all the way. And this is clearly a geometric series with a common ratio of x. Okay, the x is your common ratio. If you take the second term, x, and divide it by the first term, 1, x divided by 1 is x. X squared, the third term, divided by the second term, x squared divided by x is x. Common ratio is x. The geometric series, this geometric power series, converges when the absolute value of x, okay, the absolute value of the common ratio is less than 1. And that means the series converges when x is between -1 and 1, and then it diverges when the absolute value of x is greater than or equal to 1. Okay, so now, and I just wanted to repeat that. I wanted it to be in the recording too. But now let's go ahead and get to this example here. Okay, let's get to this example. Okay. We want to find the radius and convergence, the radius of convergence and interval of convergence of this power series. Let me give you a moment to copy it down. Okay, so we want to find the radius of convergence and interval of convergence of this power series. Power series where n equals 1 to infinity of -1 to the nth power times n squared times x to the nth power over 2 to the nth power. Okay, so is this a geometric series? Is this a geometric series? The answer is either yes or no. That's right, Robin. Definitely not. Definitely not. So how are we going to then figure out the interval of convergence? Well, first what I want to do is I just want to, just to make it a little more concrete for you, let's just see what the power series looks like. Okay, and what I've done is I've written out the first 3 terms. So again, the point of that, it isn't like something that is needed in the problem, but I think it makes it just a little more concrete. This is a power series. When you simplify the first 3 terms, the power series is going to equal -x over 2 plus x squared minus 9/8 x cubed, and plus and so forth. And hopefully I haven't made any errors. When n equals 1, this is your first term. The next term, n equals 2, that's that term. And then when n equals 3, this is the third term. And you simplify those terms and you get this. So we wish to know, and definitely you can see it's not a geometric series. We wish to know for what values of x the power series converges. So, all right, let me give you a moment to copy that. Just a moment here. All right, so let's see here. So we have this interesting power series here. It's not a geometric series per se here. It's not geometric. It doesn't start off acting like a geometric series, but maybe when n is large, this series might act like a geometric series. Remember, convergence or divergence of the series is not dependent on the first, 1,000, 100, 1,000, 10,000, million terms. The convergence of the power series depends on how the series behaves, how the terms of the series behave when n gets very large. Okay, so like for instance, if we were to go out 1 billion terms in this series and look at the billionth term and the billionth first term and the billionth second term, and those terms acted like the terms of a geometric series, of a convergent geometric series, I might add, then that we could find out for what values of x the power series converges. Does that make sense before we move on? All right, well, how are we going to do this? Oh, okay, John. So we know that our power series does not start off acting like a geometric series. It does not start acting like a geometric power series. However, if you were to go out far enough in the series, like to the billionth term, and after the billionth term, the billionth first term, the billionth second term, and so forth, if those terms of the series if the series started looking like a geometric power series, we could then find out for what values of x this series converges. Because the convergence of the series is dependent on how the series behaves when n is very, very, very large. Okay, does that make good sense? You're welcome. You're welcome. What test did you learn that is there any particular test that we can apply here to this power series? That might help us determine if it is a G, if it eventually looks like a, if we want to determine if this power series eventually resembles a convergent geometric power series, what test do we need to apply to this power series? What test from section 8.4 that you learned do we need to apply? That's right, Robin. Very good. The ratio test. We're going to apply the ratio test to this power series. Okay, and so let's do that. So we'll let the nth term, be the term of the power series. And we look at the limit as n goes to infinity of the ratio of the n plus first term over the nth term. And we want to see if the limit of that ratio approaches a number. Or I should say approaches a constant. Let's think of it like that, approaches a constant. Okay, so let me give you a moment to copy. The n plus first term here, all I did was replace all the values of n in my term by n plus 1. And then the nth term here, I just wrote the nth term below in the denominator. Okay. All right, so of course, we have to reduce this. We have a complex fraction here. We have a fraction divided by a fraction. So we'll take the top fraction and multiply by the reciprocal of the bottom fraction. And then what I like to do, my approach, is to group like terms together, as you see that I've done in this step here. We can reduce, of course. We can reduce that. -1 to the n plus first over -1 to the nth is -1 to the first power. You subtract the exponents because the bases are the same. Okay, similarly, I can reduce the rest of this fraction appropriately. And so the limit as n approaches infinity of the absolute value of the n plus first term over the n term equals the limit as n goes to infinity of -1 to the first times n plus 1 over n squared times 1/2 times x. All right, and I will move to the next page then. Does everybody have this copied down okay? Does anyone need more time? Okay. Okay. Well, let's proceed. So now the limit as n goes to infinity of the ratio of the n plus first term to the nth term, the two is equal to limit as n goes to infinity of the absolute value of n plus 1 over n squared times x over 2. And then the absolute value of this product is the product of the absolute values. You know, and again, I could have absolute values around the n plus 1 over n squared, but n plus 1 over n squared is already positive, so I don't really need those absolute values there. And n plus 1 over n is 1 plus 1 over n quantity squared. And so that will approach 1 squared. It's not, now I have this limit. I have the limit here. And then I'll take the limit. Well, the absolute value of x over 2, does that depend on n at all? No, it doesn't. So we can just leave it there. That's right, John. Good. It doesn't. We can just leave it there. So, or you can actually bring this out in front of the limit if you want, or you can just leave it there. But when you take the limit, then you're going to get 1 squared times the absolute value of x over 2, because 1 plus 1 over n as n gets large, 1 over n goes to 0. 1 plus 0 squared is 1 squared. And so the limit of the ratio of the n plus of the limit of the absolute value of the ratio, okay, the n plus first term to the nth term is equal to the absolute value of x over 2. X over 2 is your common ratio. So this power series that we're working with does act like a geometric power series when n is large. It does. It acts like a geometric power series whose common ratio is x over 2. Okay. So by the ratio test here, our power series converges when the limit of the ratio, okay, which is absolute value of x over 2, when our power series converges when the limit of the ratio, which is the absolute value of x over 2, is less than 1. Are there any questions so far? Geometric series converge when the absolute value of the ratio, common ratio, is less than 1. Our common ratio for our power series, as n gets large, our power series behaves like a geometric series with common ratio x over 2. So, well, Josiah has a good question. We need to consider all x values, and right now, let me just go to the next page. when the absolute value of x over 2 is less than 1, this means that x is between, that x over 2 is greater than negative 1 and less than 1, so x is between negative 2 and 2. So our power series does converge when x is between negative 2 and 2. We could substitute in any x value between negative 2 and 2, plug it in for x in the power series, and that series we would get would be a convergent. But like Josiah is asking, what about other x values, like when x equals 2? Are there any more x values where our power series converges? Well, one thing I'll mention, we're not going to consider values of x where the absolute value of x is greater than 2, right? Or I want to be, hold on, I want to be more clear here. No, I don't want to do that. Give me. Okay, so these x values are safe when x is between negative 2 and 2. But what about all the other x values? Well, what about if the absolute value, what about the x values where the absolute value of the common ratio is greater than 1? Okay, that would mean that the absolute value of x is greater than 2. So that would mean those would be x values for when x is greater than 2 or x is less than negative 2. Well, those x values, over those x values, the power series diverges. Okay, so I'm going to put a kind of a big X there. These x values, when x is greater than 2 and x less than negative 2, for those x values, the common ratio, the absolute value common ratio is greater than 1. So even though our power series behaves like a geometric series, when n gets large, the values of x such that the common ratio x over 2, the absolute value of x over 2 greater than 1, those values of x will not, our power series won't converge for those values of x. Let me phrase it another way here. So, you know, our power series behaves like a geometric power series with common ratio x over 2. Now, when the absolute value of x over 2 is less than 1, or equivalently, when x is between negative 2 and 2, our power series converges. But when the absolute value of x over 2 is greater than 1, or when x is greater than 2 or x is less than negative 2, our power series would have to diverge. Okay? But what's left is when x equals negative 2 or positive 2. That's what's left now to worry about, because the ratio test gives no information when the ratio equals 1. And when x is negative 2 or x is positive 2, the common ratio x over 2 equals 1. So the ratio test gives no information in that case. So the question is, what do we do? What do we do? Well, what we have to do is we have to manually check if our power series converges at x equals negative 2 or x equals 2. We have to manually check it, because the series behaves like a geometric series, right? But it's not an actual, well, I want to be careful. It behaves like a geometric series, but since it isn't exactly a geometric series, we have to test the endpoints. that interval of convergence so far includes the interval between -2 and 2, but we have to test the endpoints -2 and 2 for convergence of our power series. So far, so good? Are we? Okay, thank you, Josiah. So now let's check it out. Let's see. May I move to the next page? Are we okay on the notes so far? Okay. Well, so when x equals -2, what we do is we substitute in -2. We substitute in -2 into the power series. Okay, we substitute -2 into the power series and see what happens. When we do that, you'll have, you have -1 to the nth times -2 to the nth times n squared over 2 to the nth power. So -1 to the nth times -2 to the nth powers. I want to simplify that. Well, that's just the same as -1 times -2 raised to the nth power, which is 2 to the nth power. So what happens is then you get simplification, and at x equals -2, the power series becomes the series where n equals 1 to infinity of n squared, which is 1 squared plus 2 squared plus 3 squared. And clearly the series, and it keeps going, clearly the series diverges there. So x equals -2 would not be in our interval of convergence. Are there any questions so far? Okay. Well, what about when x equals 2? For x equals 2, we have to substitute x equals 2 into the power series, and then look at what happens. We get -1 to the nth power times n, well, the series becomes n equals 1 to infinity of -1 to the nth power times n squared. So that'll equal -1 squared plus 2 squared minus 3 squared plus 4 squared and so forth. That diverges. So the power series diverges at x equals 2. So our interval of convergence will not include x equals 2. Okay, please let me know if you have any questions. Are these notes helpful in addition to the book examples, some of these details? How many find those details helpful? Thank you, John. Great, great. Appreciate it, Robin. Thank you. Thank you. Okay, so I will move to the next page then, if I may. We're good? Okay, so therefore our interval of convergence for the power series is the interval, the open interval from -2 to 2. The radius of convergence for the power series is r equals 2. So to get the radius, what you do is you take your interval from -2 to 2 and cut it in half, and that gives you your radius of convergence. So the radius of convergence, you take your interval of convergence, divide it by 2, and that gives you your radius. Now in WebAssign, you have to be very careful when it comes to figuring out if the endpoints to the interval are included. In this case, they're not, so we use open intervals. But if they were included, we would use closed intervals. And WebAssign gives you a choice. Either it's open or it's closed, and you have one chance to get it right. So you have to be a little bit careful when it comes to that. You know. All right. Are there any questions? Are there any questions at all? Okay. Well, let's get to another example here. Then, is everybody okay on copying? Okay. Let's get to another example. Here we want to find the radius of convergence and interval of convergence of this power series. Take a moment to copy it down. Okay, so we have an interesting power series here. And we could write out the first 3 or 4 terms, but I think you know how to do that. And you know, this power series is generated, there's some function that will equal this power series. It's just right now you don't know how to take the function and express it as a power series. But right now, you know, you're taking it on faith that all these power series represent certain functions. You know, maybe it's the sine or a cosine or an exponential function, something. But what you're interested here in section 8.5 is determining the interval of convergence of the power series. So we have here the series n equals 0 to infinity of -1 to the nth power times x minus 3 to the nth power over 2 times n plus 1. So just like with the previous problem, we're going to use the ratio test to determine, to help us get us started on interval of convergence. So, okay. we'll use the ratio test, and I'm going to let you just copy it down. Let me know if you have any questions. Okay, so we'll just continue here. So we're looking at the limit of the absolute value of the n plus first term to the nth term. I'm just working through the math here. It's pretty straightforward. Again, I like to group terms together and then do my simplifying. So certainly on your next exam, section 8.5 will be on there, and certainly for the power series problems, I'll want to see some work like this. Okay, and so when you take the limit, of course, you're going to get the limit as n goes to infinity of 2n plus 1 over 2n plus 3 times the absolute value of x minus 3, because the absolute value of x minus 3 does not depend on n. Okay, so when you take the limit, what's this limit going to equal when you take the limit? Two times n plus 1 over 2 times n plus 3. What does that approach when n gets large? That's right, Robin, 1. So this is going to equal the absolute value of x minus 3. That's your common ratio. For the interval of convergence, what are we interested in regards to that common ratio? I mean, what's the next step? We have to take that common ratio and do what? That's right. Good, Robin. We have to set it less than 1. And so we'll do that. We'll do that. Are there any questions so far? Any questions before we move on? Okay. Well, we're gonna, by the ratio test, our power series converges when the limit of the n plus first term over the nth term the absolute value of the, I should say, by the ratio test, our power series converges when the limit of the absolute value of the ratio of the n plus first term to the nth term equals absolute value of x minus 3 when it's less than 1. So the key is taking that absolute value of x minus 3, setting it less than 1. Well, if absolute value of x minus 3 is less than 1, that means x minus 3 is greater than -1 and less than 1. Or that's equivalent to saying that x is between 2 and 4. Are there any questions there? All right, well, so our series converges when x is between 2 and 4. Are there any more x values where our power series converges? Well, what values do we have to test manually? What values of x do we have to test manually? Two and 4. That's right, John. That's right. And remember, we're not worried. We're not worried about when the absolute value of x minus 3 is greater than 1, right? Because when the absolute value of the common ratio is greater than 1, those x values that satisfy that inequality, the power series would not converge at those x values. So that would be equivalent to saying, you know, x minus 3 is greater than 1, or x minus 3 is less than negative 1, or hence x greater than 4, or x less than 2. But those x values, x greater than 4, x less than 2, those x values we do not worry about. The power series diverges for those x values by virtue of the fact that the common ratio is greater than 1 for those x values. Or I should say absolute value of the common ratio greater than 1. So now we have to test for when x is equal to 2 or 4. And again, the reason is because for those values, the common ratio equals 1. And so the ratio test gives no information there. Are there any questions so far? All right, well, I will move to the next page then, if we're good. No questions? All right. So we need to manually check if the power series converges at x equals 2 or x equals 4. So for x equals 2, we substitute x equals 2 into the power series. And then we have to simplify what results, what series results. And this kind of work I'm looking for, of course, on your exam. You should be, I mean, this is necessary to show this kind of work. All right, so 2 minus 3 to the nth power is negative 1 to the nth power. But then you have negative 1 to the nth times negative 1 to the nth. That's the same as negative 1 to the 2nth, right? And we get down to this step here. The power series becomes n equals 0 to infinity of negative 1 to the 2nth power divided by 2n plus 1. What would negative 1 to the 2nth power equal? What does negative 1 to the 2nth power always equal? That's right, Marvelous. It equals 1. And why is that? What can you tell me about the power 2n? What kind of power is that? And I don't know. It's kind of an open question. Begins with an E. 2 to the nth power is it's an even power. And any negative number raised to an even power is going to be positive. So, you know, negative 1 when n is 0, negative 1 to the 2 times 0th power. That's negative 1 to the 0, that's 1. When n is 1, 2 times 1 is 2. Negative 1 squared is 1. When n is 2, 2 times 2 is 4. Negative 1 to the 4th power is 1. So this series reduces to this. But now we have to ask the question, does this series here, does that series converge or diverge? So we have to think about what tests to use to see if the series converges or diverges. Who thinks the series converges? The series n equals 0 to infinity of 1 over 2n plus 1. Who thinks the series converges? Who thinks the series diverges? All right, who's a little unsure? Not getting too much response here. Well, the series to me, I mean, if we were to, as n gets large, that 1 there doesn't matter too much, right? So it looks to me like, and the 1/2 could be factored out front, it looks to me to be, as n gets large, this series to be like 1/2 times a harmonic series. But I want to be formal about it. So what I'm going to do is I'm going to use the limit comparison test. This series diverges. We're going to use the limit comparison test. And we'll let the nth term be the 1 over 2n plus 1. Okay, nth term will be 1 over 2n plus 1. I should say a sub n is 1 over 2n plus 1, and then b sub n is 1 over n. Because I'm trying to relate this to a harmonic series, this series. Well, by the limit comparison test, the limit as n goes to infinity of a sub n over b sub n will reduce to a half. And therefore, our power series diverges at x equals 2, since the harmonic series diverges. Essentially, as n gets large, our series here, this series, the series n equals 0 to infinity, 1 over 2n plus 1. As n gets large, the series essentially behaves like 1/2 times the regular harmonic series. And since the harmonic series diverges, 1/2 times the divergent harmonic series would also diverge. I mean, 1/2 times infinity is infinity. So this means then that x equals 2 is not included in the interval of convergence. Are there any questions? How many used the limit comparison test for some of the homework problems from section 8.4? Maybe give me a thumbs up if you used that test. Okay, thank you, Josiah. Thank you, John. Thank you, Julia. Thank you, Marvelous. Robin, thank you. Excellent. Lots of good participation here. Okay, and Maxim also. All right, great, great. Thank you. Okay, so now we have to look at x equals 4. Okay, so no questions here. We'll move on if there are no questions. Okay, x equals 4. For that, we substitute in x equals 4 into our power series. And the power series becomes well, 4 minus 3 to the nth power is 1 to the nth power. That's always 1. And so at x equals 4, our power series becomes a series where n equals 0 to infinity of negative 1 to the nth over 2n plus 1. What kind of series is that? What kind of series is this? It's not a geometric series. It's not a telescoping series. It does have a negative 1 to the nth power in it, meaning the terms are going to go negative, positive, and therefore, that's right, Robin, we have an alternating series. That's right. Would this alternating series converge by the alternating series test? If you think about the term it would, John, that's right. The terms of the series, the b sub n term, which is 1 over 2n plus 1, those terms decrease as n gets large, so you have a decreasing sequence of terms, and the terms approach 0. So we can very confidently say this series converges by the alternating series test. Okay. And therefore, our interval of convergence is the interval that is from 2 to 4, but it's open at 2. The interval of convergence does not include x equals 2, but it does include x equals 4. And so you have a closed interval, a closed symbol there on the right. This is just interval notation. And the radius of convergence, of course, would be equal to 1. Okay. Are there any questions on that? How many kind of like these power series problems? Think they're kind of fun? Okay. Thank you, John. Yeah, and you're going to have a little time to work on some today during class. I'll make just, are there any other questions here before we move on? So remember, the key in WebAssign, I mean, of course, it's very important WebAssign to get these, to make sure that your endpoints, you know, whether the interval's open or closed, you have to make sure you are careful with that, because you only have one chance to get that. And that's an important part of the problem. So the last page here of the solution mentions something that I mentioned earlier, that you know, there are no other values of x for which the power series will converge y. And I went over this argument with you a little earlier. So I'll just leave that there. If you want to copy that, that's fine. But I discussed this earlier in the problem. So that's fine. All right, so let me get into WebAssign here. I'd like to give you some time to work on your section 8.5 exercises, which are due tomorrow. So we have half an hour here left, class. So give me one moment. Hold on here. All right, hold on. Okay, we'll just go in here and I did send an email out. Today is the last day to withdraw from the course. So, and you can, if you want to discuss anything about that, if any of you are deciding to withdraw, you can email me and we can have a discussion online before you do that. But it would have to be today. But you know, that's just a public service announcement. I'm not making any suggestions at all. All right, one moment.